Greeted everyone. So I want to review a little bit in the same fashion that I did first order equations, now second order equations, but I should stress we only have seen linear second order equations. And so they have the particular form y double prime plus px y prime plus qx y equals, and there could be a forcing function. That's the general form of a linear second order equation, but very often we cannot even deal with those more complicated equations. So let's go over a little bit what we have. Again, I'm going to present it a little bit as a flow chart. The first thing you should ask, of course, is it constant coefficients? Meaning that we have, so this particular form is, let me write it, the particular form that it would be then would be this form, right? So you, there are many ways, again, we have mentioned that in the previous, all the lectures you've seen that the different ways of writing a particular differential equation in the most convenient form to solve it. So here we wrote it without a coefficient here. So in other words, we imagine if there's a coefficient, we divide it out. Here we keep writing it because it's sometimes simpler not to create fractions, okay? Especially when it's constants, if it's constant equations, we don't do this. Here we tend to do this. It is important that you have to know because sometimes equation has some coefficient here where in the formula the assumption is that there is no coefficient. So always double check that you're in the right form. I'll point it out when we hit it. So in the constant coefficients, there is a two-step process. We do first the complementary homogeneous. And that one is through the characteristic equation. So, and I remind you, the characteristic equation is just a t squared plus bt plus c equals 0. So the complementary, so just so that we're all on the same page. With that, of course, I mean this guy, with the f is 0. Okay, so we solve this, and this now there are three possibilities. So that the three possibilities is that so d is the discriminant, and that is in this case b squared minus 4ac. The d could be positive, the d could be 0, or the d could be negative. Okay, if it's positive, we're gonna have e to the t with a coefficient here, and so the fundamental system. Let me write it like that. So where these are the roots. There, because d is bigger than 0, there are two roots. If d is 0, this is a single root, and then we have the root and the same guy but times ln t. Not ln t, times t. Sorry, I got now confused with my. Sorry, now I get myself confused. Sorry, I'm double checking here because I don't want to say anything wrong, of course, in the review. That kind of would. Right. Where am I here? No, yeah, it's not. Okay. Yes, not t. Oh, and I should. Sorry. We have been recently working with a lot of t's, so but I should keep everything in x's here. So of course the solution should therefore be with x's here. This is not. Okay, so let me correct this here. The t are the two roots, the two values of the root, which I'm not specifying here. So and this would be this one. And finally, if we have two complex roots, so I'm a little bit short here, but that's what I'm here, then we use the cosine, we get e lambda t cosine omega t, or e lambda t, sorry, it's a little bit squeezed in. Let me try to move this whole thing here. So, okay, let me write this a little bit. Okay, let me spell it out perhaps, because otherwise it's perhaps a little bit too confusing. So, okay, we have the three cases. Okay, let me write it a little bit more in the flow chart. Since we're doing flow charts, let's keep doing it. So here is D. Okay, here's my D. I actually put it here, right? Okay, and so now the question is the three possibilities. Is it d bigger than 0? In that case, we know that the roots are two roots. let's call them, I don't know, R and S. And so then the fundamental system, so a fundamental system of homogeneous equations is e to the RT and e to the ST, where these are the two roots. The second option is that we have D0. So there is a single, this means that there is a single root, so there is two roots. This means there's a root, a single root R, and then the fundamental system is ERT and again I'm writing T's and I wanted to write X's, sorry, ERX and ERXX. And then finally, the last possibility is that this D is negative. Then we know that there are two complex roots. The roots are then, so the roots are the form lambda plus or minus omega I. And then the two solutions are E lambda X cosine omega and E lambda X, omega X and sine omega X. Of course, there's functions. Okay. So this is the fundamental system then. So in each case, we have a different fundamental system of equations. Okay, that's the complementary homogeneous. And then when we are done with the complementary homogeneous, then we have f of x of special forms, E alpha x px, where this is a polynomial of degree, a certain degree, and let's call it degree d. Okay. And so again, then there are cases here that we have to take into account. In either case, what we're going to do is we're going to put y equal to u e alpha x, and that will reduce into a second order, reduces to the case of just polynomial of px. So the exponential will be gone. So you get the px, the a alpha x will be gone, but on the other side you get now so this is a variation of parameters, right? So the variation of parameter u. So this will give you a differential equation, a linear constant coefficient differential equation in u, which reduces to the case where the function, the Forson function is just px. So perhaps so this reduces to the case that f of x becomes p of x. Okay, but again, a very important part here is alpha a root? So are we in this case, or perhaps even in that case? Okay, and in this case, so okay, my flowchart is a little bit perhaps. I hope you can follow my flowchart here. So in this case, let's see what happens. In this case, u term disappears. So what is then the u? U would be a polynomial with general coefficients. So qx. This is a general polynomial, undetermined coefficients of degree d. And we have to multiply with x, if that's the case. That's how it will look like. If we are in this case, then we get u double prime is equal to px, and we just solve. So that's actually the simplest case. And if it's not, so this is well, this case, or not. Let's put it somewhere. I have to put it somewhere, right? It's not. Then we do u is equal to qx, just the qx, which is the same general polynomial here. Okay, so it depends a little bit on what alpha is, what we will do, and yeah, okay. So keep that in mind. That's constant coefficients, and so that's then we have seen what if they're not constant. So this is constant coefficients, right? So this is yes. So if it's no, yeah. So perhaps I made this in red, and that should have been, I guess, some other color, right? I shouldn't have yet used red here for what I wrote, but that's okay. I'm not going to change that. So here now, the next question then is, oh, I was doing this in orange, right? Do we know? So now can we do variation of parameters or reduction of order. And what this refers to is we need, so the complementary homogeneous. So we know one solution, or the other thing, the other possibility is we know, so the complementary homogeneous, we have, so this is, let me write it like this, one solution, and we have a fundamental system of solutions. So there's one solution, let's call that YH, and here let's call them Y1 and Y2. So you do different things. In this case, so if this is the case here, so in this case, what you do then, you write Y equals U times YH, and we do a variation of parameters. And the result will be, so what has to happen is the U term will disappear. Disappears. And so what we get is an equation in, so we get a linear equation, so we have only, so what it means, U term disappears, we have a U double prime and U prime, so we replace V by U prime, and then this becomes a first order in V prime. And then we use the methods of first order equations in V prime, okay? In V, sorry, I have taken the derivative in V, right? In first order in V, because V is in, let me write V as I write it here, in V, okay? So that's the variation of parameters. If we are in the other case, okay, in this case, what do we do then? So there are two different cases, right? What do we do then? Then we introduce two parameters. I call them U and V, or perhaps sometimes, yeah, U1, I don't know. Yeah, let me call them now U1 and U2, because I have to say in general, but in calculations it's sometimes easier to you don't use subscripts. In formulas, subscripts are very nice. In practice, you rather work without subscripts. So what does that mean? Well, you create a system, and you say, well, U1 prime Y1 plus U2 prime Y2 has to be equal to 0. That's one equation. And the other equation is that U1 prime Y1 prime plus U2 prime Y2 prime has to be equal to F, where we have written this in this form, okay? So be careful with the coefficient. If there's a coefficient instead of the double prime, then you have to divide by this. So that's a system of equations that you solve. So with whatever means possible. Right. Okay. And then finally, there's actually one more case that is not actually in chapter 5, but we did cover it. So I want to, oh yeah, there's another case, sorry. I forgot to mention this here. I said here we have a case that of this form, but we also saw the case that this was or E alpha x cosine omega x or E alpha x sine omega x. Right? This is a case that we did not discuss in the main lectures, but we saw this case when we talked about harmonic motion. So make sure that you also know how to do that case there. I cannot review everything, but and in often we wouldn't have these. We wouldn't have these exponentials, but even if we have them, and then the same problem arises. Is this? Well, what would it now be? Of course, now we're talking about, remember, a combination. This now is of this type here, right? So notice that if we are in this type, this alpha is either in this case or in this case. It never can be in this case, because alpha is a real number. Here, we are in this case. Now the question is this alpha plus omega I a root? It can only be a single root, okay? If it's a root, if it's not a root, then we do... same thing, we do this substitution, same substitution, and then yeah, so how to do this? I'll do it in blue. Okay, I'm sorry I write about it, but let me write it up here. So the question is alpha plus omega I a root. Is this a root? Yeah. So if yes, what do you do? So if yes, so let's just first say if no. If it's not a root, then you do first of all the same thing. This part is always the same. Okay. So I'm not going to discuss this. It's what happens with the u then. Then you put u is equal to a cosine omega x plus b sine omega x. Okay, as then this kind of expression, and you find a and b. If it's yes, if it is a root, then we do the same trick as we do in the real case. We put u equal to a cosine omega x plus b sine omega x times x. Sorry, this is too much. So let me try to write it a little bit, squeeze it in a little bit somewhere else. So this is no. If it's a root, yes. Then we put u equal to x times, let me put it in front and we see it right away, cosine omega x plus b sine omega x. Okay? So that is that if alpha plus omega I is a root of, a complex root, of course, in that case. And if alpha plus omega I is a root and alpha minus omega I is also a root, and it can only be, there's never the case of the multiplicity 2 that we would have in the real case, right? This distinction we don't have between these two, because there's only this case. Okay, so, right, and then I said there's one more case that is an Euler, which we discussed really in power series, but in some sense it has nothing to do with there. And that's a very special form. It looks quite similar to linear with constant coefficient, but it isn't constant coefficients. Okay, so here is the example: ax squared y double prime plus bxy plus y. So what it needs to be is we have an x squared here and x. It is very, very particular. It has to be that way. And then we know that in that case we have the so-called indicial polynomial. So in this case that would be a t times t minus 1 plus b t plus c equals 0. Don't confuse this with the characteristic equation. They're very simple, but it's different. And then again we have the same issue here. So d, so let's box it again. D is our discriminant of this guy, right? So I'm not going to spell, because it's not b squared minus 4ac. You have to work this out. You can write it up, but I'm not going to do that. So this is the discriminant. And so again we have the three possibilities. Let's make it in green, I guess. Either this discriminant is positive, it could be 0, or it could be negative. And again, the fundamental system of equations, so the fundamental system of equations will be different. In this case, the fundamental system, if we have two roots, so this means two roots. Let's call them r and s again. This would be then x to the power r and x to the power s. If we have a single root, so we have now a root r, now we do x to the r, but we cannot do it twice, so now we do x to the r times ln x. Here's the ln x that I got confused about in the beginning. And now the other thing is that you have complex roots, so this would be lambda plus or minus I omega, of omega I. And then in that case we have e lambda x cosine omega ln x. Don't forget that there's an, oh no, not e lambda x, sorry, not e lambda x. What is it here? X to the power lambda, right? X to the power lambda cosine omega ln x. And the other one is x lambda sine omega lambda x. That's the fundamental system. Okay. Let me double check this again, because I don't want to say something wrong here. You got it, right? Okay. So that's the types, okay? And so I'm going to do only 2 examples. I cannot cover all these cases, especially I'm not going to bother myself too much with these distinctions here. But they are important, right? This here, you see this different type of things you have to do. The same happens here. So it is something that you have to pay attention to. But for sake of not making this too long a video, I'm looking at 2 examples. So the first one is this one. Y double prime minus 3y prime plus 2y equals 2e minus 5x x. Okay. Now, let's look at this. Well, this is constant coefficients. So that is great news, because that is kind of almost, well, at least the homogeneous part. So let's go there. So step 1 is the complementary homogeneous. Okay, the complementary homogeneous is y double prime minus 3y prime plus 2y equals 0. So the characteristic equation is 2 squared minus 3, 2 plus 2 equals 0. So we have to factor this, and that is t minus 2, t minus 1, right? Yeah, okay. So we have 2 roots, t is 2, t is 1. So we are in this, in the most common case, of course, that's the case when we have 2 roots, when the discriminant is positive. And so we know what to do here. This is what we have to do here. We start with y equals u alpha x. What is alpha here? So again, this is important. So here alpha is -5. So it's actually not a root. So again, this is not a root, so we will know that nothing special is going to happen. Okay, so we do, I'll box it because it's always something that we have to go back to. Y is u e to the minus 5x. Okay, and we do the variation parameters, so we need the derivative, that is u prime e to the minus 5x minus 5u e to the minus 5x, and then y double prime is u double prime e to the minus 5x minus 5 times u prime e to the minus 5x, and then the derivative of the second one, that is this of the first factor, and the second factor is minus is plus 25 e to the u to e to the minus 5x. Be very careful in these calculations, because if you make some mistake there, the whole thing can be awfully big. I've seen this happen 7 times in the quizzes. Somebody makes a line mistake, and then you get basically an equation you cannot solve. Okay, so we plug this in so we get, and we know that e to the minus 5x can come out. So here we have a y double prime, so we have a u double prime, and combining these 2 guys into minus 10u prime, and then we have plus 25u. Then I subtract 3 times u prime from it, so that is 3u prime minus minus is plus 15u, and then I add 2 times y to it, that's 2u. Okay. So what has to happen? Some things have to happen, and other things might or might not happen. So t2 to the e minus 5x, so 2x e to the minus 5x. What has to happen is that this guy disappears, and it does. Okay. Does the u cancel here? No, because alpha was not a root, so u should not cancel. Let's see what we have. We have a u double prime, then a minus 13u prime, and a 44 plus 42u, and that is equal to 2x. Okay. What do we do then? Now, look. Don't do too many things, right? So what we now do is we look for a particular solution. Yeah, so perhaps I didn't say this, but I hope you know what to do, right? So we look for the complementary homogeneous, and then we look for a particular solution, and then we put it together. I didn't say, so the 2 together here, the 2 steps together, is that this general solution is the particular plus the general homogeneous. Okay. So this was the complementary homogeneous. This was, so here we calculated YH, here we calculated YP. Okay, so we now in. Okay, so we know now we're at this stage here. We know that u has to, it's this case, the case that it's not a root. So u is just a polynomial of an indeterminate coefficient of the same degree as what we have. What do we have? Degree 1. So we have to do, so this is degree, let me write it here, so the degree is 1. So we're going to do u is ax plus b, general polynomial of degree 1 in this coefficient. So we then find u prime is a and u double prime is actually 0. So that's actually doesn't even contribute. So we get minus 13a plus 42 ax plus b equals 2x. So we get minus 13a plus 42ax plus 42b is equal to 2x. So what does that mean? Well, that means that these two coefficients are the same, so 42a is equal to 2, and also that minus 13a plus 42b is equal to 0. Now, I thought the numbers were, I might not have worked this out in detail, so I don't know whether my numbers are supposed to be like this or not. Just making sure. There's a minus 2u prime. Did I not? What is? Oh. I think I made a mistake here. No. Minus 3, yeah, no. Minus 3u prime. Let me see here. Let me quickly look at my notes. Yeah, I don't know. Let's see. I think I didn't have two nice numbers. Okay, a is 2 over 42. That's 1 over 21. And if I plug this in, then I see that 13a is equal to 42b. So a is equal to b is equal to 13a divided by 42. So that is a kind of a huge number, 13 over 42 times 21 here. Okay. Okay, whatever they are doesn't matter. So now, don't forget to put things together. What is the particular solution? The particular solution is this one, right? The pink here. So this u that we just calculated as 1 over 21x plus 13 over 42 times 21. I'm not even working that out. Times e to the e minus 5x. That's the particular solution. The general solution is this particular solution. So let's copy this one. So 121x plus 13 over 42 times 21 e to the minus 5x plus the general homogeneous solution, which was, did we even write that down? No, I didn't even write it down. Sorry, I should have written down, right? So the general homogeneous was, these are the two roots, e to the 2x plus b e to the minus x. So e to the 2x plus b e to the minus x. And that's the solution. I mean, I didn't give an initial condition in this case. Now, I want to do the same problem, but using variation of parameter, reduction of order. It is somehow not perhaps the smartest way. Let's see, okay? Reduction of order. Now, for reduction of order, there is some condition. We need to, let's look at reduction of order. Oh, I didn't give the names here. This was what we called reduction of the order. And this we called variation of parameters, right? This is what we call it, right? Yeah, variation of parameters. So variation parameters. So there were two different methods, but there were a condition. We couldn't do them. There was a requirement. For the reduction of order, you had to have at least one homogeneous. For variation of parameters, we need a fundamental system. Now, we are in this case, so we can actually do both. Of course, if you can do this one, you can do that one too. This one is sometimes quicker. This one only requires one homogeneous. So let's do this one, okay? Reduction of order using, I don't know, so we use one of them. Let's use E2x. So that's a homogeneous solution, okay? So let's see what we have to do then. Then we do a same thing. Y is U a, so it is basically the same thing, right? Y is U2x. Well, it's not the same thing because this time we are focusing on the homogeneous solution part, whereas in the This case, we were looking at what's on the other side, on this e minus 5x, right? So they are totally different approaches to this problem. Okay, let's see what happens if I do this. Of course, I have to calculate y prime, that is u prime e to x plus 2u e to the 2x. And then y double prime is u double prime e to x plus 2u prime e to x plus 2u prime e to x plus 4u e to x. Okay. Now we don't know what happened. Well, in fact, you see they all have an e to x in front, so I'm going to factor it out. Although this will not cancel with what happens on the right-hand side, because that's not what the method is supposed to be doing. What the method is supposed to be doing, we'll see. Okay, let's work it out. No, let's predict it before we go. What has to happen? Remember, what has to happen in this case is that the u term has to disappear. Okay, let's see that happens. So we plug this in. Where is my equation? Oh, I don't have my equation. I'm going to copy it quickly here. It is y double prime minus 3y prime plus 2y equals 2x e to the minus 5x. Okay, so if I plug in y double prime, I get the u double prime. These two combined is a 4u prime plus 4u, then minus 3. So minus 3u prime minus 6u. You might say, we have done this already. Yeah, but there will be different numbers. The power was then minus 5x. Now there's different numbers on this side. It's similar calculation, but different numbers. Plus 2 times y, that's 2u. So remember what I said. What has to happen is the u's have to cancel. And that is exactly what happens. Now, what doesn't happen, not necessarily happens, is that the cancellation of the exponentials. So that does not happen here, unfortunately. Okay? So let's see. So what we have here, let's write down, clean this up a little bit. This is what we left, right? And then we have an e to the x here. Let me copy that still. And that is equal to 2x e to the minus 5x. And now the whole point is, because there is no u term, we can think of this as a first order in the derivative of u. That's something we have done in mechanics very often, right? So let's call it velocity, so v. So v is u prime, but again, I'm going to box it because later I want to come back to this. I should also have boxed this guy, right? Okay. So what does that mean? Well, let's write it down. E to x, we have a v prime plus v equals 2x e minus 5x. First order linear equations. Okay, professor, I think we should make it, we should divide by 2x both sides. Okay, so we get v prime plus v is equal to 2x e to the minus 7x. You see where the minus 7 comes from? Because the e to x to the other side becomes minus 2x, and then you add the exponents is minus 7x. Okay, first order, very good. First order, constant coefficient, but that doesn't matter here much in first order. So we look at the complementary homogeneous. That is, v prime plus v equals 0. So that is v prime equals minus v. That means that v dv over v is equal to minus dx. I hope you understand what I'm doing, right? V prime is dv dx, and then I bring the things to the side separating variables. We know first order homogeneous is always separating variables. So we find that the ln of v is equal to minus x plus a constant. Do we note the constant here? No, because we're looking for a particular solution, so I'm going to ignore the constant. Okay, so I should point that out here, right? No. In this case, wait. In this case, since we only have one homogeneous, we need to work with the constant. So let's keep the constant. So let's call it plus d here, because obviously I'm going to raise it, exponentiate here. So we get v is equal to e minus x plus d. So that would be e to the plus e to the d times e to the minus x. So this would be c times e minus x. Okay, so let's write it up. V is equal to c e minus x. Great. What do we do? Well, that's the homogeneous one, right? So this is the complementary homogeneous. So now this next thing that we have to do is use one of those. Oh, so I guess that's why I didn't need to see. Yeah, right. So v is a now variation of parameters, but I have u already. In this case, I cannot say, oh, it's an intermediate calculation, because no, u is there, right? So I'm introducing a w here, e minus x. Remember, what you do is you take one of these homogeneous solutions. Let me put the h here to make clear that's a homogeneous one, and you put a parameter here. So this is our variation of parameters that we're going to do here. That's the parameter, if you want. Okay. Okay. So we do v prime. That is w prime e minus x minus w e minus x, and we plug this in. The equation was v prime plus v equals this guy. So we get w prime e minus x minus w e minus x plus v, which was w e minus x, is equal to 2x e to the minus 7x. Okay, what's happening? These guys go, and that has to happen, right? Because what we have left with is an integral, really. So what is the integral here? W prime is equal to 2x e to the minus 7x, and then this becomes an e to the x, so e to the minus 6x. So we have to integrate this, so w is the integral of 2x e to the minus 6x. Dx. So this one I can do on the side by integration by parts. So that's why I can box it, integration by parts. And then can you use u and v. So u is 2x, dv is e to the minus 6x dx. So du is 2x dx. And then for v is equal to minus 1/6. Minus 1/6. Wait, did I? Sorry. Yeah, it doesn't matter much, but oh no, this is on this other sheet. Sorry guys, just want to double check here. Where do I write this? I don't know anymore. This is it, right? Yeah, okay, yeah. So minus 1/6 e to the minus 6x, right? And the derivative of that. So this integral is equal to uv minus integral v du. That is so minus 1/3 e to the minus 6xx minus plus du is 2 dx. Okay, so plus 1/3 e to the minus 6x dx. Okay, and the 2 and the minus 1/6 becomes a minus 1/3, and to bring that out, and then with the minus becomes a plus 1/3. So this is equal to minus 1/3 e to the minus 6xx minus 1/18 e to the minus 6x. I have to divide. I hope you see where the 18 comes from, right? So, okay, it's 3 over negative 6, right? Okay, so, yeah. Okay, so where were we here? So this guy, w, I'm going to write this here, right? W is equal to minus 1/3 x e to the minus 6x plus, no, minus 1/18 e to the minus 6x. That is w. Now, remember, w, I should have boxed that again. W comes from this guy. So v is equal to minus 1/3 x e to, now I multiply this with e minus, so minus 7x minus 1/18 e to the minus 7x. Okay, what's that? Well, we go to v. V is u prime. I think I might have actually put the wrong f here. I cannot find my notes anymore. Where did I do this calculation? Sorry guys, give me a sec to find my calculation back. What is is my calculation. Did I make mistake here? Sorry, let me double check. Yeah, yeah, I see here. The numbers are not so nice. I apologize for that. So what is V here? So V is double. Yeah, we know V, but what is V? V is U prime, right? So we have to antiderive this guy. I apologize. This is a little bit of antiderivatives here. We have to do the integration by parts again. Okay, and then we. Yeah, I'm sorry. I wish the numbers were nicer, but they're not. I just took some numbers and now I'm stuck with it. I don't want to change them anymore. So what we now have here is we have to integrate this. There's the integral over this whole thing here. So minus 1/3 x e to the minus 7x and integral minus 1/18 e to the minus 7x dx. Okay, so this is again a partial fractions. So we have to do this again here. So I'm going to not do the minus. Let's do only this part here. So here u is x, dv is e to the minus 7x dx. So du is dx, and v is e to the minus 7x over minus 7. So this is equal to uv minus integral v du. That is equal to, so this is in between, x e to the minus 7x plus 1/7 e to the minus 7x dx, right? This minus 1/7 comes out. And if I interderive this one more time, it's x to the e minus 7x minus 1 over 49. And I'm missing a 7, right? This is also has to have minus 7 here. Okay, so this is minus 7, and this is minus, minus 149 e to the minus 7x. Okay, so this is minus 1/3, that guy, which is x e to the minus 7x over negative 7, or let's put a negative here, minus e to the minus 7x over 49, minus 1 over 18, and this one is just e to the minus 7x over minus 7. Okay, this is u prime, and what is u now? Sorry, this is u now. Sorry, this is u. Sorry, u prime was, sorry, this was u prime, right? So this is now u. We integrated it. So this is u, and so y, now go to our last, this one, we have to multiply this with e to x. So this would be, now there are, okay, let's look at the coefficients here. We get, so this is u times e to x, okay? So we, first of all, the first coefficient is 1 over 21, and we have an x e to the minus 5x, because I'm adding the 2x onto the minus 7x, right? And then here we have two coefficients, of e to minus 7x. Well, so this becomes, so what are the coefficients here? Okay, one of the coefficients is 1/3 times 149, and minus 1 over, plus 1 over 18 times 7, and that is e to the minus 5x. Okay, so perhaps on common denominator here, well, okay, that is my y, and let's see what my solution is. We kind of, here, we have it here, right? I'm not going to check. I'm hopeful that is, well, I see that the first number is correct here, the 1 over 21, right? And this one, if I put it on common denominator, you want me to do it? Okay, I'll do it. And the common denominator is supposedly 42. Well, yeah, okay, 42 times 20 times 21. No, I don't want to do this. I'm confident it's the same. Okay, of course, it's different methods, so it presents the answer a little bit in different case. Now, remember, this was a particular solution that we have, and oh, we didn't. sorry, and that is because I did not take into account my constants. Okay, this is important. So the first time I integrated this, created this constant here. Okay, so if I that is w. So now remember, w was times ex. So this was c to the e minus x. Okay, so sorry, I have to do the constants now. So let's pay attention to the constants. So this is what I'm going to add here. The first time integration is c. Now this is the formula. So I have to multiply this with e minus x. So I get this term here. So if I end the derive here, this will be minus c to the e minus x plus a d. Okay, so in here we would have also, so u here we would have minus c, but that's a constant, so I'm going to call the constant a minus x plus b. So this is u, so I have to add this to u, these two constants here, right? There's the c and the d here, minus c and d, which I call now a and b, just to, and now I multiply this with e to x. Okay, so if the result of that will be plus a times e, 2x minus x is x, plus b e to the minus 2x. So you might have wondered, where is the homogeneous solution? That's where it was. Okay, and this is exactly what we see here, right? In the first way that we solved it, where was the solution? Yeah, here, these two. Okay, yeah, a and b. Oh, what is with the minus signs? Did I copy this wrong? The roots were what? 2 and 1. Yeah, I don't know why I had, oh my god, did I do this whole problem wrong? This has to be a plus 1, right? The roots are 2 and 1. Did I use this? No, I didn't use this anywhere, right? This is just a copy error. Okay, that's just a copy error. No, I didn't use this here. And did I use it here? I know, I luckily used the one that was correct, not the wrong one. Oh, good thing, good thing. Okay. I said, sorry, you multiply here with 2x, e to the 2x. So you multiply this with e to the 2x, that is this and that. Sorry. So it is, everything is correct. I just was a bit messy. Okay, I don't want one more. This is this one. I think in this one I kind of was more careful with the numbers. Now, let's think about this. This is not linear, this is not constant coefficients. So what we need to do is reduction of order of variation of parameters. And Euler, by the way, I should point this out, we only have done homogeneous. So an Euler equation is always homogeneous, at least as far as the way that we have dealt with it. Now, okay, so what are we dealing here with? Yeah, this is Euler. This is exactly these powers of x that we have here, but it's not homogeneous. Yeah, but that's okay. If I solve the homogeneous one as an Euler equation, I know how to do that. And then, if I solve it as an Euler equation, I can use variation of parameters or reduction of order. I can use either one, right? Because I've solved it as an Euler equation. So that's what I'm going to do. So this is a problem that we have not seen. So that's why I wanted to add this. So step 1 is the complementary homogeneous. That's a kind of a step we always do, but this time it's not a constant coefficient one. So this is an Euler equation. If it's an Euler equation, we look instead to the initial polynomial and not the characteristic. Okay, so that would be t times t minus 1 minus t minus 8 equals 0. Okay, so that is t squared minus t minus 8 equals 0. So it's t squared minus 2t equals minus 8 equals 0. Sorry, now I want to make sure that I copied this one right. Oh yeah, right. So this factors as t minus 4, t plus 2, right? Minus, yes, okay. So we get two roots. T is 4 and t is negative 2. So what does this mean? It's an Euler with two different roots. It's the simplest, the not tricky part, if you want. So we are in this part here. It's two powers here. Okay. So the two powers that we have are, so the fundamental system, or the general homogeneous solution is a times x to the fourth plus b times x to the negative 2. Yes, okay. That is the what happens with Eulers. So we have both now. So I'm now going to do, I could do reduction of order again, but let's do variation of parameters so that we also practice that. So I'm now going to do variation of parameters. I don't have anything else. Can I do anything else? You say, well, Professor, is this not kind of a polynomial thing? Well, first of all, it's not a polynomial because it's in the denominator. But even so, this technique here, so you might think you could do this whole bit here, this whole long thing that we discussed here with either this form, oh sorry, it's a little bit messy here, or this forms, right? These were the particular forms here. But that only works if it constant coefficients, which we don't. So, okay, so we cannot do that. So we do variation of parameters. And so variation of parameters, remember, this means that you're actually gonna look at the particular system, this particular system here. Okay, let's write down what the system is in this particular case. So we have, what this means is instead of this capital A and capital B, we're going to have now two parameters. So our system is going to be u x to the fourth plus v x to the minus 2. That is what we're going to try to find. This is how, so a particular solution will be of this form. But do not plug this in. What we say now is we have a system of equations. The system is, well, you take the derivatives of the two parameters and this with the same functions, the homogeneous solutions functions, and you put this equal to 0. And now you take the derivative of those guys. You keep this one, but take derivative of x to the fourth, that is 4x cubed, plus you couple that one, and take derivative of that is minus 2x to the minus 3. And you put this equal to the forcing function. 13.6 over, sorry, I think this had to be 36. Sorry, let me. Yeah, I think there was no x squared there. I'm sorry, the x squared, I wrote it in the, this is after so this was supposed to be 36, just like that. So that is equal to 36. Okay. So let's see here, we can solve in the top one here, right? Let's solve for u prime x, or let's solve for v prime perhaps, that is less. So okay, so I'm going to use the first, so v prime over x squared is equal to minus u prime x to the fourth, bring that to the other side, and then bring the x squared to that side. So v prime is equal to minus u prime x to the sixth. And now I can plug that into the second equation. So we get 4x cubed u prime minus 2 over x cubed, let's write it in the denominator, and then v prime is this guy, minus u prime x to the sixth, and that is equal to 36. So the x cubed with the x to the sixth cancel to an x to that one, and then we have a 4x cubed minus plus 2, so we get a 6 x cubed u prime equals 36. I hope I did everything right here. Right. I have to solve in u prime, so this means that u prime is now equal to 6 x to the minus 3. And now I integrate. So I do u is equal to the integral of this thing, 6x minus 3 dx. So that is 6x to the, add 1 to the exponent divided by the exponent. And what do we do with the parameters? Always have to think about that. Let's think. What how this technique works. So let's go back here. Where did I discuss it here? In this technique, right, we have the homogeneous system, we have it, so we only need a particular solution. Okay, and then we put it together in the usual way. So no, I'm not going to bother with the coefficient, with the constants here, and so we get minus 2 x to the power negative 2. That is u, and so what do we do now? Well, we have v prime, and so we calculate u prime. Well, we know what u prime is. U prime is 6x minus 2, so this is minus 6x to the minus 3x to the 6th. So that is, this is v prime, right? And so this is equal to minus 6x cubed. So we see that v is equal to minus 6x to the 4th over 4. So v is equal to minus 3/2 x cubed. X to the 4th. I don't know why I said x cubed. What do we do with these two guys? Well, we have solved them. So we're going to plug them into the formula here, that what I should have boxed. So this is the formula. This gives us y. But there is a different thing happening, right? We don't use that. We use this system of equations that we solve, and that gives us the solution. So we see now that y is equal to, let's see, you have to put the right thing by the right thing. So u, that's u, minus 2x minus 2 times x to the 4th. And the other one is plus v. So minus 3/2 x to the 4th times x to the minus 2. So what does this actually give me? That is actually minus 2x squared, and this is minus 3/2, also x squared. Actually, so it all cancels out a little bit. So this is minus 7/2 x squared, seems to be the solution. So this is a particular solution, right? So I'll write it now as write it here. My particular solution is 7/2 over x squared. So what is the general solution? Well, that's the particular solution, 7/2 x squared, plus the general homogeneous, which had right, ax to the 4th plus bx to the minus 2. Okay, so this is something that you have to be prepared for. It could well be that you get an equation that is Euler but not homogeneous. And in that case, you solve the homogeneous as an Euler equation, and then use either variation of parameters or reduction of order, whichever you prefer to do. Now, variation of parameters is quicker. You saw this was rather quick that we do this. If you would do, I'm not going to do it, otherwise the video is a bit too long. But if you do this with reduction of order, you see it is a little bit more steps in calculation, and therefore easier to make mistakes. Okay, so that is our lecture on how to solve second order equations. I've not talked about you can solve them also using power series, which I didn't discuss in this video. That's for next time. And neither did I talk about applications of these things when we in harmonic motion. So that's there, of course. This is most of that case is about constant coefficients, right? Okay, so that is for the review for linear second order equations.